All right, good afternoon, everyone. Press what? Okay, merci. Any questions before I get going? Yes. Les corriger? Je pense Fatemeh va arriver plus tard et discuter. Okay, so we're going to talk about classes today. So as we said at the beginning of the course, Scala is a functional and object-oriented language, and it's really that marrying of the functional and object-oriented paradigm that gives Scala its unique flavor. So here is a simple, somewhat pointless class to show the basic mechanics of how classes work. So when you first look at it, you say, okay, it's a class point. That's not particularly surprising. It has here a method called move. It has a method distance from origin. It has a method toString. So it's kind of like a class in Java or C++. And so the basics are, of course, the same. You know what a class is. You know what methods are. And the syntax is Scala-ish. You use def to define a method. And you put the parameters inside here. There's an equal sign to compute a result. So none of that is very surprising. Let's look at the things that are a little bit surprising. First of all, you notice here that in the definition of toString, there's the keyword override. So in Scala, whenever you override an inherited method, what we inherit here is the toString method from the what in Java would be the object superclass, then you have to specify override to indicate you're going to redefine that method. That's something that's possible in Java as well with an annotation. It's a safety feature. Sometimes people accidentally override something. Sometimes people mean to override something and they make a slight mistake somewhere with a parameter or the return types. And so here by saying, I intend to override, the compiler can give you good warnings about that. What I always do, coming from Java, is I forget to put it in, and then the compiler says, you should be putting override here, and then I do. There's no law that says I have to get it right the first time. So the other thing that's notable is, notice that this method here has parentheses followed by parameters. This method over here, you see it's a method because of the def, but it doesn't have any parentheses behind here. So it's considered the Scala way to not put parentheses for methods that are not mutating methods and that have no parameters. So this method just computes a value that depends on the state of this object, doesn't take any parameters. So that's considered something that's kind of like it's a computed attribute, and you don't put parentheses. Same thing with toString. Even though, of course, in the superclass it was defined with the parentheses because it was inherited from Java, we don't put the parentheses here. If you had a mutator method, which we haven't discussed yet because you don't yet know how to mutate, then if it had no parameters, you would put the parentheses as a matter of style. Now, where are the instance variables? Normally in Java, you're used to the fact, or in C++, that there would be some variables defined inside the body of the class. But in Scala, one tries to define them up here as parameters of the class. So this means that every point has two instance variables, x and y, and the val indicates that those instance variables are values, they're immutable. So this is an immutable class. You can't mutate the fields, and all of the methods, don't even try. Notice that the move method here returns a new point. So when we're moving a point, the current point is unchanged, and a new point is returned that would be the target of the movement. That looks a little bit odd at first, maybe, but it is the Scala way to make classes immutable when you can. As an unrelated aside that has really nothing to do with classes, but it's a convenient notation that I need for today. There is a special form of strings in Scala called interpolated strings. If a string starts out with the S prefix, then inside it you can put in a dollar sign followed by any expression, just like you can, for example, in Ruby. So you would say dollar sign, and inside there you put an expression, and then that expression gets evaluated and spliced into the string. So here the toString method makes a pair, like parentheses 3, 4, for example, if x is 3 and y is 4. So that's the basic thing on how classes tend to look like. So you have methods like usual defined with def. This thing we'll see on the next slide. You have this special thing with that a method without arguments doesn't need the parentheses, and you have the oddity that the instance variables appear up here. There's a bit more to it, as you'll see next. So part of the notation with putting the instance variables on the top is that when you do that, you automatically get a constructor called the primary constructor. So over here, we said x and y are up here as parameters of the point class, and they automatically become parameters of this primary constructor that's built for you at no extra charge. So you can construct a new point as new point 3, 4 here, or whatever. And so the nice thing about this is, if you think about what you have to do in Java or C++, there's always a bunch of busy work that you have some fields, and then you have to write the constructors, you have to write accessors, field accessors, and so on. And of course, in Eclipse, you just control space your way through that, and it types it in for you. But you still have to read it, and so Scala tries to reduce that busy work to the absolute minimum. So when you have a class, and you have instance variables, you automatically get a constructor that initializes the instance variables. What if you want other constructors? Well, those you then have to write by hand. So here I have another constructor, and that's the one over here. Notice that the name of the constructor is this, whereas in Java and in C++, the name of the constructor is the same as the name of the class. Why is it dumb to have the same name of the class and the constructor? Did you ever write a class and then 5 minutes later you decide that was not a good name for the class, and then you had to change it? And then you have to change the name of all of the constructors. That's dumb. There's no need to do that. So in Scala, they have a much smarter arrangement. They say if you want to have another constructor, you call it this. That way, for whatever reason you need to rename the class, you don't have to go through and rename those. And this is a special keyword anyway, so they didn't have to come up with a keyword for constructor or something. It's right there. So that's that's smart, and it's easy. Yes?
Can you go back?
Yeah.
Can you write new this, or do you have to...
No, that is a good point. You do have to write new point. That would be an interesting change. Yes, I like it. Okay, I'll have to ponder that and see whether that's possible, and then we'll let Martin know. So you can write new constructors, and the only thing is you have to call the primary constructor in all of these auxiliary constructors, which is what you would expect. So ultimately, all the construction goes through the primary constructor, but you can invoke it out of convenience. This particular example is maybe not that convincing because there's another way that you can implement that. All functions and methods in Scala can have default arguments. So over here, when you write equals 0, here and here, that means that if you don't supply the parameters, then a 0 gets automatically supplied. And so you could just use that feature instead of using an auxiliary constructor. And truth be told, that is quite common. One doesn't write auxiliary constructors as often as you might think. Now, another thing that's maybe not all that common, but it's interesting, is you can put code into the body of the class. So here I'm putting this print statement into the body of the class, and that code is automatically code of the primary constructor. So when one parses a class, you kind of have to split out all of the defs. That's the method definitions. And any code that's staying in there, that is code that gets run as part of the primary constructor. And so the way that Scala people like to think about a class is that a class is just like a function. It can have code in it. It can have variables. So these things are like parameters of the class, so to speak. I'm not sure that's all that helpful when you first come to see it. So I think when I first saw it, I just took this as a super shorthand. And say, we just don't want to write the constructor, but if the constructor does need to do something extra, you just dump the code right into the class. Philosophically, one could see it the other way around and say, but I'm not going to belabor that right now. So a couple of differences from Java and C++. So in Scala, we prefer to have immutable classes, but it's possible to have mutable classes if you want to. If you want to, then the instance variables have to be labeled with var instead of val. And I don't think we've seen var so far because we've tried to not do any mutation, but it'll happen in a couple examples in today's lecture. So here it is. Try not to use it though, and in general I'll tell you when it's reasonable to use it. The other thing we have is what's called the uniform access principle. When you have an expression such as p.x, where p is a point, then what it means in this particular case is we want to access this instance variable here. We want to get it or we want to set it. But that's actually not quite true. You don't really know what how p.x is implemented. Is it a direct field access? Is it a method call? That's something that behind the scenes it can be one thing or the other, and you can, as you'll see in the lab, you can change from one to the other. And that's kind of nice because you can start out a class that starts out simple and with just instance variables, and later you might decide that you want to protect the getters and setters and re-implement them, or you may want to re-implement the class, keeping the public interface the same and changing the private implementation. And then what used to be just a field access now has to be a method call. And all of that is transparent to the client. So, yeah.
Can you store instant variables as like by name variables, like functions with the arrow?
So you mean if you put an arrow here?
Yeah.
My hunch is no, but I'd have to try it out.
I'll try to
Yeah, because what would it mean? So, I don't understand what it would mean. It would mean you would pass something on to it that would only be evaluated later. Okay, I don't think so. But we'll try it out. So, another thing is when you first learn C++ or Java, they tell you, you should make all of your instance variables private. Public instance variables are bad, bad, bad. And then some people are saying, getters and setters are bad. If everyone had a getter and setter for every instance variable, then that's the same thing as having them all public. And in Scala, we kind of say, relax. First of all, there are many, many classes where really all of the instance variables are exposed. And in Java, it is a big fat pain. So if you do, for example, database programming in Java, and you build yourself an entity class, it really is your intent that the entity class reflects everything that's in the database table. And it is a true pain in the neck to have to write all of the instance variables and the getters and setters for all of them. Yes, I know Eclipse does it for you, but it still is a pain. And so in Scala, one says, what was the reason for that fear? The reason for the fear was that when you expose all of this stuff and then you want to change the representation, then some of these instance variables may have gone away. Some of them may be more restricted. But since we have the uniform access principle, it doesn't matter. We can, when we change the implementation, we can set up a set of methods, of these parameterless methods, that give us the illusion that the instance variables were still there. And so in practical cases, that's just about always easy to do. And so one should kind of overcome that unreasonable fear of getters and setters and that exaggerated feeling that everything must be encapsulated. I mean, encapsulation is good, but it can be driven to an extreme. And so Scala tries to have, I think, a very practical approach to saying that, in those cases where you pretty much know that instance variables are the way to go, or they're easy to replace, you as the programmer should be allowed the wisdom to do that. So you can, on the other hand, if you wanted to do it the private way, you can declare any private variables that you like. So here's an example. So you don't have to do anything with the primary constructor and the vals and vars that are declared up there. You can declare whatever you want as private. And so it's up to you which mix of strategies is the best one for a particular class. Finally, you can have in the primary constructor, you can have variables that are not defined as var or val. So over here we say when constructing a point, it is necessary to supply an x or y, but we're kind of coy about where the x and y are actually being stored in the class, whether they're instance variables. For sure, when you do it like this, without the var or val, you're not going to get the accessors. So when you later have a point, you can't just say, hey, point, what was your x? If you wanted that, you'd have to use a val or var. The Scala compiler will now optimize away. If the x and y are only needed while the constructor runs, they will not be turned into instance variables. But if they're needed in some other functions that refer to them, then they will in fact be turned into private instance variables. Yeah?
And those, during the execution of the constructor code, are they val or vars?
Well, they're neither. They're just variables that are, they're just parameters of the constructor. So if you look at the val or var, let's look at the var up here, they kind of serve double duty. On the one hand, they really are instance variables, and they're also construction parameters. When you omit the var and val, they're only construction parameters. And they do not give rise to, they certainly do not give rise to these public instance variables.
What I meant is, are they mutable or not? Like
Oh, you can mute just like any parameter. I don't even know. Where the parameters are mutable. Oh. No. So in Scala, no parameters are mutable, and so they're also not mutable. So the parameters, the only question is, what is their lifetime? Do they get captured for later? And they get captured for later if you reference them in some other methods. So you would do this if you need some other construction parameters that you don't want to have as public instance variables. All right, so let's put this to work. And so my question is, over here we have a class mystery. How many instance variables does it have? Well, if you don't have the cards, you're just going to have to say it when I ask. All right, let's do. Okay, so we have almost universal. I can't see this. What? B? Okay, so we have a bunch of B's and a bunch of C's. So let's go through this here because I forgot. So the candidates for instance variables are x, y, and z, right? So x for sure is an instance variable, right? It has a val. So no discussion there. With y, well, we'll check that out in a minute. What about z? Yeah, it's an instance variable. It's a it doesn't automatically get an accessor, but it's still there. And so the question is, what about y? So, and to answer that, we need to know, do we need to retain the value, does the class need to retain the value of y after construction has finished? So we'll make ourselves a new mystery of 17 and 29. And do we need to know what this 29 was after construction was finished? So be the primary constructor. The primary constructor sets z to the sum of the two. And then it's finished. The method that we have, the only other method, that's foo. That's really the only thing we can do with this thing later. We can ask it m.foo. Okay, we can also ask it what's m.x. So those are the two things that we can do with it. Neither of the two things requires y. Neither of the two requires that the class hangs on to y, and so it'll be optimized away. So y is not an instance variable, and that means we have two instance variables. Yes?
Can you go back to the previous slide?
Yes.
So it doesn't really give rise to a private instance variable.
Okay, that is true. That is true. So I need to write in here. Very good. If needed. Okay? Yes. Excellent point. Okay. If I forget to do that, someone send me an email, please, and say, fix your slides. Okay, more about methods. There is a nifty infix notation that we already looked at a couple of lectures ago. So whenever you write x, then the name of a method, and then y, without any parentheses or dots, that is the same thing as x dot op of y. And that's, of course, the Scala way, since it saves 3 symbols. So, for example, 1 to 10 is the same thing as 1 dot to of 10. So, you'd have to fill in these things. There's a dot here, parentheses here, a dot here. Here where we have the parentheses, a dot here. So these dots can be put in or omitted any way you like. This is particularly useful with methods that are arithmetic symbols. In Scala, a method name doesn't have to be letters and numbers and underscores. It can be also a sequence of symbolic characters. So there's a specific definition of what symbols are. There's like a collection of a dozen or so of what you normally consider symbols, and also any Unicode symbol can be a symbol in Scala. Any chain of those symbols can make a name. So here we have just one. So I could define a method called asterisk, and in this case I'm scaling a point by a factor. That's just to have some reasonable context. And when I call that method, I can call it the old-fashioned way with a dot and the method name and the parentheses, or I can call it in the infix notation, which is, of course, much clearer. So that simple rule is very nice. That means in Scala there's actually no difference at all between operators and symbols and methods. Every operator is a method. Every binary method is an operator, and so it's it makes Scala very uniform. It makes it immediately obvious on how you define any operators you want. It also means that people go wild and crazy with operators. That in C++ you can overload a small number of operators. In Java, operator overloading was forbidden. Why? Does anyone know why? Why does Scala not have any way for you to define multiplication of big numbers or matrices or some such thing? So the Java designers felt strongly about this. They said, hey, in C++, people went wild and crazy with operator overloading. That you could write C++ code by defining crazy operators, and no one could understand later what that thing did. And in Scala, it's much more so, because you can come up with your own operators, and you can be wilder and crazier than you could ever be in C++. The difference, though, between Java and Scala is that Scala was designed for people with taste and restraint. Whereas in Java, the image of the programmer is one who has neither and who must be restrained forcefully by the rules of the language. So in Scala, we should choose our, we should wield our power wisely. We should not translate everything into operators. I mean, you could probably spell out, I don't quite know what the rules are, but I believe you could spell out like the names of all of the methods in Morse code and use that as operators, and that would probably not be a good idea, so people don't do that. And generally, the library designers have, I think, done a pretty good job in not going wild and crazy, but having a reasonable set of these operators. There's a couple of tactical things. Generally, operators associate left to right, particularly mathematical operators. But once in a while, you need an operator that associates right to left for one reason or another. And the way you do that in Scala is by the special rule, which sounds a little arbitrary at first, but it works out nicely in practice. If the operator ends in a colon, it associates right to left. Now, the only operator that I could think of that is naturally right associative is raising something to a power. So if we wanted to have an operator for raising to a power, we would have raising to a power is right associative, because when you have a to the b to the c, you want to do this stuff first. That's just the way it works mathematically, because after all, a to the b to the c this way is the same thing as a to the b c, so there's no need for having the parentheses. And so if you wanted to do this in Scala, you would have to give it some name that ends with a colon. Like if you wanted to have a Fortran or Python-style star, you would have to add a colon to it. Now, this thing looks weird enough that this is not actually done in Scala. Like I said, taste and restraint. But you could do it like that. We'll see in the next unit a natural example for a right associative operator that does end in a colon. There's a couple of special rules, and the most important one is that if you wanted to overload the function notation, like what you have for maps, if you remember, if you have a map and then you just say parentheses and the key, that's something special, that's something that you can define. And you define that not by defining a method called just parentheses. I guess they could have said, def parentheses, but that's just too weird. And so they gave that the super special name apply. So that's one of the few rules that apply is another way of overloading just the function application. Objects. So in Java and C++, you have static methods, and you have static variables, and those are always a little bit weird, and so Scala has a prettier way of giving the same thing. So they call something that has, so if you want to have a static variable or a static method, you put it into an object. An object is a class with a single instance. So here we have an object that I call accounts, and it keeps track of the last account number that was ever seen, and then it has a method, a mutator method, that updates the last number and gives it out. So that way you can have consecutive accounts. Note the parentheses behind here. This thing is a mutator. It changes the state of the object. So I put the parentheses there to make that explicit. So you can use this accounts object any way you want. You would just say, if you needed a new number, you would say accounts dot new unique number. And there you'd have a new account number. And so it's an object. So accounts is this object. It is the sole instance of this thing. So why do I like it better than static in Java and C++? For one thing, it's convenient to just put these kind of oddball static things into a separate pot instead of mixing them up with the rest of the class. And also, I just always dislike the keyword static. Why is it called static? Does anyone know? What does it mean to have a static method or a static variable in C++ or Java?
Does it have something to do with the stack of the key or something?
No. So when you learned Java or C++, did anyone tell you why it's called static? So to understand why it's called static, you have to go back into the deep history of C. In C, you have two kinds of local variables. You have automatic and static variables. Automatic local variables are put on the stack, and static variables are put in the static data area, so they don't go away when the function returns. It's an oddball function, feature of C that I think is almost never used. But there it was in 1970. In C++, then they had a completely unrelated issue. They wanted to have what normally is called a class variable, a variable that only exists once per class. And they needed a new keyword for it. But they didn't want to introduce a new keyword because there's always a high cost of introducing a keyword into an existing living language, namely that if that keyword had been used anywhere else, then that code would no longer compile. And so C++ was built on top of C, and they're always very nervous about introducing any new keywords. As I said, well, static is no one ever uses static for anything, so we'll just use static. And that's the honest truth. So that's why these features were called static. In fact, when there was a point later in time when Strostrup introduced exception handling to C++. And he was very unhappy about that exception handling seemed to require two keywords, namely try and catch. And for a while he tried to do without catch. And it was only try. And it made it very hard to actually read anything. And a bunch of us tried to convince him at the time that he could actually get away with using static for everything. And that was so ridiculous that he decided to go for try and catch after all. So static is this universal keyword that's used whenever they have something else that they don't want to introduce a new keyword for. And that's where it comes from. So it's nice that Scala did away with that nonsense, and we have this thing with the object. There's one special object that one needs once in a while. We haven't used it because in the worksheets we don't need it. But eventually we'll be moving off worksheets and we'll write actual applications. And C++ and Java do this very ugly thing with public static void main, which is another static. And also, why have a special thing? So Scala does this much more elegantly when you have an application that extends this special thing called app. Then that is your application. That is your main. And so the code in the primary constructor of this object gets executed when you want to execute your program. So that's a nice and clean way of not having that oddity of the main method. Now, it often happens that you have a class, and then you also want to have some associated, what you've so far seen as static methods. Then you give the class and the object the same name. You put them into the same source file, and then they call it the companion feature. So you have a companion class, the companion object, and you've seen that in Scaladoc. Let's look at vector, for example. You see in the symbol where you see the O peeking out behind here. When you click on it, you get the code for the companion object, the companion class. Okay, so these belong together. They actually have access to each other's private features. And there's a common idiom where you, instead of having the constructor syntax, you put an apply method into the companion object. And then that way, you can, and so that thing is a factory. It's a factory for the for the class, and so the method calls new, but then you don't ever have to call new in client code. So 0.3 comma 4 is, yeah. Now, admittedly, had they had that brightly earlier, they could have made that automatic. And as we will see later, it is automatic in certain classes. So that's a common thing that you'll see. It's prettier than always having to call new, particularly when you use it with an operator notation, right? When you write new 0.34 times, that somehow looks weird because the new makes you think of it as if it was a pointer. But here, this is the point at 3.4, and you multiply it with something. It looks very natural. So I'll very briefly talk about traits. We're not going to be needing them for a little bit very much, but so that you know. So in Java, you have this phenomenon that a class can extend a single superclass, and it can implement any number of interfaces, but you can't do very much with interfaces. Now in Java 8, you can do a little bit more, but in traditional Java, interfaces were strictly abstract. In C++, of course, a class can extend any number of superclasses, and then you can get very complicated rules when you have naming conflicts in the superclasses. So Scala has a different take at that. That works quite nicely, and it's somewhat more dynamic. So in Scala, a class can only have one superclass like in Java, and that's forced by the limitations of the virtual machine, but it can extend any number of things called traits. So a trait is just like a class. It can have methods. It can have abstract methods, which would then force the implementing class to put something in, or it could have actual implementations. In fact, traits can have variables. So traits can have state, unlike even in Java 8, the interfaces. And so you can extend as many traits as you like. And some classes actually extend quite a few traits. Here, look at good old vector, and it extends 1 to like 6 or 7 different traits. And so that's considered the Scala way, that you want to put functionality into independent units, and then you want to mix them in to construct something bigger. There's only one thing that a trait cannot have. It cannot have construction parameters. And I knew at one point why, but it's not worth getting into right now. So you should think of a trait as kind of a unit of functionality with some behavior, where the intent is that it gets mixed in with maybe other traits into a class. So I have a typical trait here. I have a logger trait. It has a method log, and by default, it'll just print out the log message. Then I could extend the logger, and then I now have access to the service. So if I want to log something, I just say log, and I have it available because I'm extending this thing. Now, I can define refined versions of this trait. So here I say a logger with a timestamp is just like a logger, but I'm going to override the log method and say print the current time, or I shouldn't say print, I should say log the current time, whatever logging means. It could be to a file or whatever. Log the current time, and then the message that was intended to be logged. And I can have a short logger here where I just truncate the method to 15 characters, or as you'll see in a minute, one can even change this thing later. So I can refine what it means to logging, and now I can do something that you can't do in either Java or C++. Now I can mix in these things, and the order in which I mix them in determines what actually happens. So I say, give me a point with this and this trait. And now let's see what happens when we move this point. The move method calls log, so it's not going to say log moving whatever this 0.34 to whatever. And now, since the move method calls log, that now kicks into the logger. What logger do we have? We have a timestamp logger with short logger, and it goes right to left. So the short logger happens first, and it truncates this thing to 15 characters. And then it gets passed into the timestamp logger that adds on the timestamp. So you have this layering effect, and it's completely dynamic, that when you define these individual traits, you say super, this would make no sense in Java at all, because well, I guess I shouldn't say that. So what happens with super is it's dynamic. It depends on how the traits are layered in a particular instantiation. So let's just practice that and see what happens if we do it the other way around. And so work through this in your mind and tell me what gets logged. All right. Yes. What gets logged? Okay. Okay, B. Okay, so we have some mixture of B's and C's. Let's find out. So it goes right to left. So the timestamp logger kicks in first. The timestamp logger is going to attach a timestamp. And then the short logger kicks in, and it's going to truncate that to 20. Notice that I can override a val, which is a little bit weird. What that really means is that what I'm overriding is the accessor. And so previously, in the code over here, it was 15. Right here it says val max length equals 15. But over here, when you call max length, it actually calls into the accessor. The accessor is dynamically invoked, and when you override it, it'll now check for 20. So now what it's going to have to do is going to have to truncate the timestamp to 20 characters. And so I guess this was the one truncated to 15 characters. No one got full. Very good. And so B must be the right answer. Now, someone said C. Does anyone want to explain why they said C?
Yeah.
Okay.
Because counting from moving, well, it applies the short order first. So the whole message would be for me moving 3.
I see.
comma 4,
So you thought it goes left to right.
Yeah.
Yeah, and it's intuitively that might make sense, but it just there's a technical advantage why right to left is the right choice, and one just has to remember that to apply these things right to left. Why is right to left? I can't remember, but yeah, there's when you it applies a linearization algorithm to the traits, and the way linearization naturally works right to left. I have to remember why, but I did work it out in my mind once, and then I forgot. Yeah.
I just have a question on the previous slide.
Yeah.
Regarding the S prefix for strings.
Yes.
First, I can see that we dropped the curly braces, like $X, $Y.
Yes. So there's a special rule that I neglected to mention, that if the thing behind there is a single token, then you can omit the curly braces.
So this leads me to my next question. So we can just put like $curly braces and then a new Java date. Would it work?
Yes, totally.
Oh.
Oh, that would have been so much better. Yes. So this would have been much better. I should have done S instead of this ugly concatenation, right? So dollar new, yes, and then space, and then dollar MSG. Yes, that would have been better. And here quote. Yeah. Yes, I should fix the slide. Excellent. This is a relatively new addition to Scala, and yeah, and I don't always use it. But generally, I think it's much easier to read it. All this concatenation with a blizzard of pluses is always a little hard. So I should definitely change that. Very good. So then we have a lab where you fuss with a class. And so this is an important exercise where we're going to be talking it to death after you're done, where you change the internal implementation, and you'll see what consequences that has, and we'll have a little bit of fun with operators. All right, let's get right to it.